Okay, so here's what we were talking about last time. It's an application of the chain rule to dealing with different coordinate systems. So suppose you have some function, maybe that's written in terms of rectangular coordinates, right? But you'd like to understand its derivatives in terms of polar coordinates, let's just say, or vice versa, right? So this, I'm just going to do the one example, but this kind of idea of connecting derivatives with respect to one coordinate system to derivatives with respect to a different coordinate system is very important, because sometimes functions are really easily expressed within one coordinate system, but really easy to talk about, natural laws of, how physics works, how does heat flow, how do waves move, this kind of thing, with respect to a different coordinate system like rectangular. So we'd gotten down to this point here. We made the observation that once you've taken the partials of z with respect to x and y, right, those expressions themselves are also functions of x and y. And so very naturally then they sort of go into the diagram like this with these arrows. That highlighter is really too blunt. These arrows like this. Right? So zx is a function of x and y, zy is a function of x and y. And so you take this expression, apply the product rule. This one, product rule, gives you this. Note that these two terms are 0. We talked about that last time. So all you're left with is these terms, and thus we have ourselves down to here. Okay, so this is where we pick up then. What do we do with this expression? We'll start by looking at, again, one term at a time. What do we do with this term? Well, the cosine theta just kind of sticks around. That's pretty easy. The hard part is, what is this next derivative? What is the partial of zx with respect to r? And so notice where these two variables are in the diagram. I'm treating zx as a variable. I mean, it kind of is. It's an expression, function of x and y that I can give a name to. So treat it like a variable. It kind of is a variable. So its partial derivative with respect to r, well, there's two intermediate variables. There's two terms here that we're going to get then in the chain rule. X and y are the two intermediate variables. And so notice here's what you might call the x term, and there's sort of what you might call the y term. Right? So that partial derivative, immediate application of the chain rule, two intermediate variables x and y, gives you that this partial derivative is the sum of these two terms. That's kind of this is the nut, if you will, of this calculation. This is the hard part, I guess, is making the insight that there is a requirement to use the chain rule. By the way, don't make another classic blunder that I see students do sometimes is they'll take this thing that we have circled in green here, and they'll just write it as ZXR and just call it a day. And that doesn't make any sense. Z is a function of x and y. You can talk about the partial of z with respect to x, but as soon as you say, well, now I want to take the derivative with respect to r, you're saying I want to view this as a composition to take that derivative, but you haven't done that derivative. Right? So this doesn't really make any sense even. This notation where we use subscripts to represent variables you take derivatives with respect to is intended only to mean, for input variables that are part of the same space. So x and y are part of the same space, right? R and theta are part of the same space, at the same sort of level in the composition of these functions. So you can't mix those derivative variables like that. So whether you want to call this nonsense or incomplete, either way, it's unacceptable. So don't make that mistake. Okay. All right. So likewise for zy, right? If you want to take the partial of zy with respect to circled the wrong thing. Partial of zy with respect to r. Well, then again, there's two intermediate variables, x and y, thus giving you these two terms, and so that partial derivative is this. And of course, sine theta sticks around. Same idea. All right, is everybody happy? And at this point, it's all over except for sort of simplifications. I'll go ahead and comment on some of those. Let's look at what we have there. The partial of zx with respect to x, that's zxx. Right? The partial of x with respect to r, well, we talked about that last time. X is r cosine theta. It's always the same formula, and if you're representing x in polar coordinates. So you can just straight up compute that. It's cosine theta, etc. on down the line. You multiply things out and collect terms, and this is what you get. Here's your generic formula for how to take if you have some function z, some function of x and y. In other words, if you know how to compute rectangular derivatives of z, then this formula here allows you to compute a polar second derivative of z. Yep.
Well, I guess the only way that you could replace that zxx cosine squared theta plus zyy sine squared theta using the identity would be if it was the same code.
Yep, they aren't, so you can't. Yeah, it doesn't. Yep, close but no cigar. Yeah, as they say. Yeah. Yep.
What's the condition for zyx equals to zxy?
Right, quite right. Let's see. So I should have said here that this function has to have continuous second partials, and I didn't say that, so shame on me. That is a requirement for that to be true. Yep, good point. Okay, everybody happy? See how this process works? The big trick, my opinion, is not only make sure that you have an initial roadmap of what variables depend on what, so that you can see when am I going to have to use the chain rule and what are the intermediate variables, but don't forget to append, once you've taken one set of partials, with the new variables that you've in effect created by taking those partials. Make sure to note what they're functions of as well. Okay, and then that being done, just slowly, carefully, don't forget the chain rule, and it'll all fall out. Okay, so there's some homework exercises where you're going to do that kind of thing. So I'll leave those to y'all. Next thing we're going to talk about is implicit differentiation. I'm going to start with a question that y'all have probably all seen in high school calculus class. Here's a curve. X squared plus y squared is 25. And there's what the curve looks like. And here's a tangent line at a particular point that we're given. And how do you find the slope of that tangent line? And a common sort of knee-jerk reaction is for students to say, oh, slope of tangent line, that means the derivative. And students will just take the derivative of the first thing they see and declare that to be the answer, right? So a lot of students will take and say, all right, well, I guess this is the function. And they'll take the derivative with respect to x and get 2x. Declare victory. All right, so this is wrong, right? This is very wrong. Specifically, slopes are derivatives only if you're talking about the slope of a graph, right? And very importantly, this curve over here is not a graph. It's not even close to a graph. Not only is it not a graph because of this issue, vertical line test problems, that can be dealt with, it is certainly not a graph of that, right? It is a level set of that. And so this is the classic blunder that I see. Again, a lot of students make this mistake if they use the calculus of graphs, but they're applying it to level sets. Makes no sense at all. It's completely wrong. Everybody see the catastrophe, the potential there? Okay. Right. So let's talk about how to actually deal with this problem correctly. It's not a graph. This is a minor problem. It's not a graph, but look, I'm really only interested in the slope of the tangent line to that part of the curve. I could throw away the majority of this. I could just scratch all this off and say, you know what, forget that. I don't, that's in my way. What a bother. I don't need that. Let's just throw that away, and let's ask, what is the slope of the tangent line to this curve right here? And that curve passes the vertical line test, no problem, so problem solved. So now we have a graph. This curve is a graph. It remains, however, that we're not viewing it as a graph. It is still the case that this curve, the only algebra we have for this curve is x squared plus y squared is equal to 25. So I do not have this as y equals. Now, I know that in this case, we could, right? The algebra that would be involved here to go through and solve for y, at this little piece of curve around the point that's in question is doable. So what I want to do though is entertain the question of what if it weren't? Now you might say, well, why are we tying our hands unnecessarily? Well, look, I could come up with an example where this algebra is impossible. Right? It's not even that hard. Make it cubic, put an exponential of y in there, and the algebra would be, you could not solve for y, right? So that's out there. That's what we really are interested in, is these slightly harder problems than this one. I want to start with this easy one, and deliberately let's, avoid the little sidestep here, because I don't want to get bogged down in the algebra. Right? And I want to be able to make certain intuitive references to this specific curve, to circles. We all know about circles. There's certain geometric features of circles, and I want to be able to talk about those geometric features so that when we come up with a result, we can say, yeah, that result is right. That's what we should have gotten. Right? So for that benefit, I'm going to ask us to momentarily look aside, pretend we didn't see that. Right? Let's pretend we cannot solve for y as a function of x here. Okay, so what do? We can't solve for y as a function of x. Well, I'm just going to assert that even though I can't solve for it, it passes the vertical line test. Y is some function of x. I'm going to call it y of x because it is y, and this is a very common sloppiness that we don't need to worry about. So it is some function of x, and I know that x squared plus y squared is 25, and so altogether by taking this function of x that I don't know what it is, and by plugging it into the equation that I know is satisfied for every point on this graph, right? What I have then is a statement about single variable calculus. Right? And so what we have circled in this equation here is a new function, great big function of x. And I can talk about its derivatives. At which point you might say, okay, but that's not the function whose derivative I want either. Right? So why are we bothering to compute the derivative of this thing? And just, so follow me through. The reason we take the derivative of this thing, you're quite right. We don't really care about what that is. It's easy to do, though. The derivative of x squared is 2x. The derivative of y squared, don't forget y is a function of x. Don't forget to use the chain rule. Right? Computing this derivative that we don't care about makes the derivative that we do care about show up as part of an equation in which I can solve for it. And there's what I wanted. Yeah? Everybody happy? So, another one of these little mathematical bank shots. We get where we want to go by seemingly starting off in the wrong direction, and then we end up getting where we wanted to go anyway. Okay. All right, so I think y'all probably saw this argument in high school. The way you probably saw it in high school was this, given this algebra. And, okay, let's take the derivative of both sides, right, just right off the bat, and then solve for the thing that you care about. Right, and then plug in the point that you're interested in, right? We're looking at the point 3, 4, so when x is 3, y is 4, plug that in, and that gives you the slope we want. Right? So has everybody seen this in high school? It's what they call implicit differentiation. Right? Okay, so I wanted you all to see the ideas that underlie this. We have to recognize that there's a bunch of stuff going on. This is a level set, not a graph. We have to recognize that we are throwing away most of the curve and looking only at a nearby part of the curve, so that we can declare that y is a function, so that we can then do the chain rule. And then, of course, everything after that's sort of algebra. Okay. But it all crashes and burns if you can't declare that y is a function of x. Right? So that's a really important part of this problem. Now, I have deliberately glossed over a worry This is a serious worry. This is not going to always go away. And I glossed over it on purpose because partly for dramatic effect and partly because I wanted to, we'll worry about it later type situation. So here's what I've glossed over. I have asserted here with no justification other than y'all know what circles look like. I have just asserted that this curve, if you look at that point and if you look at a part of the curve near that point, I just asserted that is in fact a graph of some function. How do I know that? Right, well again, we know what circles look like. Sure, fine. But in general, if we play this, suppose it's not a circle, suppose it's some wacky equation involving cubics and exponentials and whatever, and we don't know what this curve looks like, are we sure that for every point on the curve there's going to be some I just take some little small little bitty little piece of the curve and that it's definitely going to be the graph of some function, it's definitely going to pass the vertical line test? No, we can't be sure. And in fact, I am sure that sometimes you can't. In fact, even on this curve, that statement does not hold up. Take this point on the exact same curve, still, circle of radius 5. That point there, right on the side, where y is equal to 0, x is 5. That point, I don't care how small of a little piece of curve you focus your attention on, it is going to fail the vertical line test. So if you're charged with the task of here's some equation, here's some point, let's say it's this one, and that you don't know anything about the shapes of circles, and find the slope of the tangent line at that point. If you just say, okay, so I'm going to assert that y is a function of x, and then from that I'm going to go do a bunch of algebra. You have written something down that is not true. You've written down garbage, right? This is bad. Mathematicians don't ever want to write down garbage. It's one of our rules, right? So that's what we want to figure out how we can avoid, right? Most of the points on the circle have the feature that, if you look at a small little piece of curve near that point, okay, it's going to pass the vertical line test. But some of them don't. This one fails. Why does this point fail? Well, we'll get to that in a minute. But the reality is that there's nothing you can do to save that point. You can never declare that part of the curve to be a function of x. And so this business here, you cannot write that down. It's not that the answer is wrong. It's that every step in this process is meaningless, nonsense garbage. Everybody see what I'm talking about? This is a nasty worry. Okay, so how do we deal with that? We've already talked about most of that stuff. So here's a picture. Now notice I'm not drawing a circle here. I don't want to. Let's not make assumptions that all curves have the same sort of qualitative features as circles. So here's a brand new wacky curve. Who knows what it is? Notice all I'm assuming that I know about it is that it is a level set, right? Okay. And let's think about points like this, problem points. That is a problem point. This point here has the feature that I don't care how much you restrict your attention, no matter how little of a piece of curve around it you look at, it will fail the vertical line test. This is not a graph. Y is not a function of x in any sense near that point. The problem is, the thing that makes that a problem, I appeal to your intuition, is that the curve has kind of wrapped under itself at that point. That is the instant at which the point is wrapped under itself, and it's the fact that it has wrapped under itself that is causing the vertical line test, which hits there, to also hit there, and thus fail the vertical line test. So the wrapping under itself. Now, if it's wrapping under itself at that exact moment, that means that it has a vertical tangent line. So if it's a problem, if the point that we are interested in is a problem, it will have a vertical tangent line. Now, we still don't know which points these are, right? So we can't declare victory on this. We don't know which points are problems and thus have a vertical tangent line. Right? Okay, but here's what we can also say. If it has a vertical tangent line, then don't forget, by the way, that since we're looking at a level set of some function f, the gradient of f is going to be perpendicular. Right? Gradients are perpendicular to level sets. This is one of our big conclusions from last time. Gradients are perpendicular to level sets. So if the tangent line is vertical, that means that the gradient is horizontal. That means, don't forget how you compute this gradient. This gradient is partial of f with respect to x, partial of f with respect to y. And that being horizontal means that this is 0. Okay, so if we, in fact, have a point that is a problem means that a certain partial derivative is 0. Everybody on board so far? No, we're still not quite done. Not quite done. We're still trying to figure out, we want a statement that goes the other direction. I don't want, if I have a problem, then a certain thing will happen. What I want is, hey, if a certain thing happens, then I can proceed with no problem. Right? So I want, in some sense, the exact opposite of this statement. And so we do what's called the contrapositive. And let me write this down. Just to sort of summarize, problem implies partial of f with respect to y is 0. The contrapositive says if the partial of f with respect to y is not 0, no problem. Is everybody comfortable with this contrapositive argument? You know, if P implies Q, then not Q. Well, let's think about that. Wait a second. If Q is not true, how could P be true? If P were true, Q would have to be true. So if Q is not true, there's no way P could be true. Yeah? Everybody see what I'm talking about there? So not Q implies not P. So the contrapositive of this statement here is whenever the partial with respect to y is non-zero, I know for sure I don't have a problem. Everything's fine, and I can declare y to be a function of x, and I can proceed with the high school calculus process with a, clear conscience. Yeah? So that's this is called the implicit function theorem. This thing right here. So if you're looking at a level set, and if the partial with respect to y is non-zero, then y can be thought of as a function of x. The implicit function theorem doesn't tell you anything about how to find y prime. It just gets you over that one little hurdle of, wait a minute, did I just write down nonsense? Right? So it tells you that, yes, you can go ahead and call it a function of x, and that then you still have to do the implicit differentiation. Right? Okay. So this just kind of gets over that one little hurdle. So here's an example. So this is the same example we looked at previously. And by the way, on an exam in this course, if you apply implicit differentiation, this is what I want to see right here. In other words, the sloppiness that is tolerated in a single variable calculus class because, well, they can't really do this in a single variable calculus class. They don't know about gradient vectors and level sets. There's a lot of tools that we use here that they just don't have access to. So they can't do any better than sort of how it's presented. But I want to see as follows, given a curve with an equation, you want to find the slope of the tangent line at a certain point. The first thing I want to see is that you take the function whose level set you're looking at, take the derivative with respect to y, and confirm that it's not 0. Right? Then you can say, by the implicit function theorem, I know that this variable y can be thought of as a function of x. Having done that, then give me the same old stuff that you used to do in high school. This is totally fine right there, and we've already walked through the details of that, and there's the answer. Okay, is everybody happy? Okay? So do keep in mind, as a multivariable calculus course, what we're interested in here is not, the purpose of these kinds of questions is not to test specifically with, all of this discussion whether you remember a technique that you learned in high school Calc 1. Right? That's not what we're doing here. The point here, that what makes this appropriate to a multivariable calculus course is that there is a multivariable calculus aspect to it, and it's the confirming that in fact this is what we say it is that comes from the implicit function theorem, sort of the first half of this this solution. So this right here, in fact, that is what we're interested in mostly. So on an exam, just historically speaking, it would not be unusual for me to make it, at least half of the points of the question are, did you confirm what you were supposed to confirm? And then, okay, sure, I guess maybe up to half of the points might be, can you execute the resulting details? Alrighty. Quick observation before we go on. There's a multivariable version of this. There's a one dimension up version of this. Actually, there's more than that, but we're going to talk about one version up. Notice that there's a certain function. There's a certain variable that we would like to be able to treat as a function. I would like to be able to treat y as a function, right? We've got this algebra where x and y are kind of on equal footing. They're both just variables within some algebra, but there's one of those variables I want to view as a function. Notice that the one that I want to view as a function, that's the one that I take the partial with respect to when I'm applying the implicit function theorem. Right? There's something a little bit counterintuitive about that. We know that here's what used to bug me. Aren't we trying to find the partial with respect to x? We're looking for slope. So am I not looking for the partial, for the derivative with respect to x? Ultimately, deep down, that's a derivative with respect to x. Shouldn't I be taking the derivative with respect to x here? No. This is a completely separate question. What we're doing up here is trying to figure out if we can view y as a function. This is not, what I've got in yellow here is not part of the calculation of slope. It's part of the determination of whether I can view y as a function. So but make sure not to make that. That's another very common mistake that I'll see students do. It happens every year that students will take this function and they will take its partial derivative and confirm that it's non-zero, but they took the partial with respect to x. It doesn't make any sense either. Okay, so make sure to get that straight. Okay, so let's talk about the multivariable version. Suppose you have some multivariable equation involving lots of variables, right? And you want to find a certain slope of a tangent line to a cross section, right? So you're the way the question is going to be phrased, you're going to feel like I just want to compute a certain partial derivative. Same situation, the function that I'm given, I'm looking at a level set of it, not a graph of it. Right? So how do you know that the thing that you would like to declare to be a function of the other variables, in this case, how do you know that it actually is a function of the other variable? So let's look at an example of this. I have a picture drawn down here. It's not in the book. This is supplemental. Anyway, y'all can just a quick double check. I am recording this. Okay, so y'all can get this figure in the recording, or you can take a picture with your phone or whatever. So here's the idea. I would like to say, hey, here's a point that I might be interested in, and yeah, okay, sure, the entire surface might not be a graph. It might fail the vertical line test, right? But all I'm really interested in is what's happening nearby a certain point. Nearby that point, I'm really only interested in, just what's going on nearby. And nearby that point, we pass the vertical line test. So let me just declare z to be a function of x and y, and we'll start taking derivatives. And when the algebra's over there on the left, we'll start talking about the algebra in a moment. But we have to worry about the same problem that we're worried about in the single variable case. Just because most of the time nearby we'll pass the vertical line test and therefore have a z as a function of x and y. That doesn't mean it always happens. And so here's the case where it doesn't happen. Look at this point there. That point where there's a vertical tangent plane. Right? Near that point, I don't care how much of the rest of the surface you ignore, any amount of surface that encloses that point is going to fail the vertical line test because this surface is in the process of wrapping under itself. Right? So we'd have a problem. And roughly speaking, the exact same argument identifies when that problem happened. If there's a problem, vertical tangent plane. Vertical tangent plane means that the gradient of the function whose level set we're looking at will be horizontal. And if that gradient is horizontal, that means that this partial would equal to 0. And so we find ourselves in this same situation. Problem would imply that the partial of f with respect to z is equal to 0. That partial of f with respect to z being the third component of that vector there. Right? That is going to be horizontal. And again, the contrapositive says that if the partial of f with respect to z is not 0, then no problem. So this is how the what you might call the three-dimensional implicit function theorem works. And again, the variable that you want to view as a function if you want to write z as a function of x and y and start taking partial derivatives and start doing, just kind of algebra, whatever function you want to view, whatever variable you want to view as a function, that's the variable that you take the partial with respect to, confirm it's not 0, and then declare that yes, you can view it as a function. Yeah, everybody on board? See the analogy? It's kind of, in that way, it's just like the single variable version of the theorem. Okay, so let's look at the algebra specific to this question. This question, we're looking at that equation. It's x squared plus y to the 4th plus z to the 6th is equal to 3. And we're looking at that point. You can check that that point satisfies that equation. So that's a point on this wacky surface. And what's the slope of the tangent line to a certain cross-section specifically perpendicular to the y-axis? And then let me come down here and draw another picture. I need a little bit of space to work. So we've got some surface, and we don't know what this surface looks like. We can speculate that it's vaguely sphere-like. But anyway, it's some surface. We're looking at a certain point on that surface. And we're looking for the, slope of the cross-section. Cross-section perpendicular to the y-axis. Okay, so let's come down to the picture. Here's the y-axis. Cross-section perpendicular to the y-axis is, let's see here, art challenge. Perpendicular to the y-axis, we're going to have some curve, some curve like that. We're looking for a slope of a tangent line to this curve, and I appeal to your intuition now. If I were, geometric intuition, if I were viewing z as a function of x and y, that cross-section being perpendicular to the y-axis means I'm looking for the slope in the x direction. What I really want here is partial of z with respect to x. That make sense? You always got to analyze these things. Don't just assume, well, the question said this variable, therefore I need to use that variable. You got to think about the phrasing of the question, interpret, make sure, draw the geometry if you have to, make sure you're understanding the question correctly, and interpret appropriately what is the thing you actually have to compute. So we're computing the partial of z with respect to x. Two things you need to know about this. First of all, it is the partial of z with respect to x. So I have to take the partial of f with respect to z. I have to take the partial of this thing here with respect to z. and confirm it's not 0 before I can just declare that z is a function of x and y. Everybody see how that's the first step? Everybody see how I chose what to take a partial of with respect to what? That's the key point here. Okay. All right. So there's that, and then let's see here. Now that I know that z is a function of x and y, now it's really just algebra. But it does remain that this is algebra where you've got to think carefully what you're dealing with, right? So this is algebra where where z is a function of x and y. And I'm taking, let's see here, I'm interested in computing the partial of z with respect to x. So I'm going to take my initial equation and take the x partial of both sides so that the thing I'm interested in will show up, right? So that this thing will appear. So what that means then is that as I go through this algebra, I'll leave it like that. As I go through this algebra, z is a function, x is the variable, and y is a constant. Y is a constant because I'm taking a partial with respect to x. Is everybody okay with that? Okay, so keep that in mind as you're going through and doing this algebra. Okay, so that said, our initial algebra was, I'm just going to write it as a reference here, x squared plus y to the 4th plus z to the 6th equals 3. And let's see here, we're taking the x partial. X partial of x squared is 2x. X is a variable, so that's cool. That's how that works. Yeah. Okay. Now wait a second. What is the partial of y to the 4th? Lots of students write down 4y cubed. Right? Well, no. It's not 4y cubed. Y is a constant. We're doing a partial with respect to x here. So we treat y like a constant because it is a constant. Right? Another common mistake students will make at this point is that maybe they don't write 4y cubed, but they might say, oh, well, we're taking, it's y, but we're taking a partial with respect to x, and so we've got to use the chain rule. So some students will put down 4y cubed times y prime, which is completely, technically it's true because y prime is 0, but it's completely unnecessary to write it that way because that y prime is 0. And the students who do this don't then subsequently plug in y prime equals 0. They just have this extra meaningless term floating around in their algebra. So don't make that mistake either. Okay. Lastly, what do we do with this z to the 6th? That z to the 6th, well, here's where we have to use the chain rule, because z is a function of x and y. Right? That was kind of the whole point to the first half of the problem. Z is a function of x and y. We're taking a partial with respect to x, but we're taking a partial of z to the 6th. So z to the 6th is a function of z. Z is a function of x. There's a chain rule situation. So don't forget to put in there's a single variable chain rule because we're holding y constant. There's no intermediate. There's only one intermediate variable, but nevertheless, chain rule. Okay, so this is these 3 steps. There's sort of each one of these 3 terms got treated pretty differently in this algebra, right? And lots of students mess that up. Now, just in order so that we could focus on what was happening to these different variables, I made this algebra such that the x's and the y's and the z's were kind of all separated from each other. But think about what would happen if you had like x squared y. What do you do with that? Well, y is a constant, so that's easy. What if you have x squared z cubed? Well, x squared is a function of x. Z cubed is also a function of x. So there you've got a product rule situation. So you got to deal, there's little algebraic situations like that are going to come up. In fact, they'll come up more often than they won't. This is sort of arguably a relatively simple example, but be on the lookout for the natural algebraic complexities that'll arise. Okay. So we are going to do a jump in the book. In the book, the next section is about optimization. The next 3 sections are about optimization. And you may have noticed this on the lecture schedule, but I like to leave these 3 sections to the very end of the course. Roughly speaking, the reason for that is that these are, roughly speaking, the only 3 topics that are not part of the prerequisite trail of Chapter 6. Chapter 6 is kind of what we're all leading up to in this course. We're building up to being able to deal with Chapter 6, vector calculus. And so, and it's a tragedy that the material that is kind of the most geometrically challenging and where there's most need for discussion comes right at the end of the course. Standard problem. In fact, it's especially bad in the summers, because summers are so packed together and move so fast, and it has happened before that students will learn material on a Tuesday, last day of class, that it's the hardest material in the course, and then the final exam is Wednesday. Right? It's insane. That's oh my gosh, it's highly undesirable. So the one thing that I can do about that, now fortunately because our final exam's on a Sunday, so I think we have like 2 days of gap in there, and that's nice, but it's still, right? Still. What I can do is I can take anything that's not in the prerequisite trail of Chapter 6 and move it to the very end, then everything else gets to push forward in the course, and that gives us more time. So rather than learn, the hardest part of Chapter 6 on a Thursday and have the final exam Sunday, we're going to learn the hardest part of Chapter 6 on Tuesday and then have the final exam Sunday. So that gives a much appreciated extra buffer amount of time to absorb those hard ideas. Does everybody see my motivation? Yeah. So anyway, we are going to skip the next 3 sections here momentarily. We will come back to them on the last 2 days of class. I think Thursday is the last day of class. I forget. And we're going to move on now into Chapter 5 on integrals. Okay. So the first thing I want to talk about is to make sure everyone understands what single variable integrals are, and I know you all have some degree of understanding of single variable integrals. I think a lot of students, just based on my experience historically speaking, extrapolating, I'll bet you a lot of you might misunderstand some things about single variable integrals. And so I feel like we need to get that straightened out first before we go on. A lot of students misunderstand what an integral is. A lot of students think that the definition of an integral is the area under the graph of a function. And it's really importantly not true. You could argue that maybe this was the first application. You could say that this is the motivation, maybe, for the definition of an integral, but it's really importantly the case that this is not the definition of an integral. An integral is a Riemann sum. So this thing here, right down here. That's the definition of an integral. It's this algebraic construction. Now, you might be thinking to yourself, this is just mathematicians being upset about, abstractions and minutia that don't have anything to do with the real world. And I will confess there's a component of that. Right? Mathematicians love that kind of thing. Okay, but that's not why I'm making a big deal out of it in Math 212. The reason I'm making a big deal out of it in Math 212 is highly strategic. It's highly motivated by I want y'all to be able to solve applications. Okay, so let's talk about other applications other than finding the area under a graph, which I seem to have erased the little circle there. Let's suppose you want to talk about, you want to compute the amount of work that it takes to build a building, and there's this classic situation of, the parts are on the ground, and I'm going to have to lift heavy stuff up to height, some of it to more height, some of it not very high. So I've got a whole work equals force times distance situation going on, but there's different distances, right? Not all of the force goes up the same distance. So how do you deal with that? And, what you can do is you can take that question and you can break it up into little small tasks. Namely, how much work does it take to build the first short distance? Well, everything that is on let me just roughly say the first floor, it's all being picked up pretty much the same amount. right? And all the stuff that's going to the second floor its distance that it's being lifted is approximately the same amount. And you can break the problem up into little pieces, and then you can write that the total amount of work is the sum of the amounts of work that you associate to each little piece. In other words, you write down a Riemann sum. That's what a Riemann sum is. And you look at the expression here, where we have a sum where we're going to take the limit so that our slices, our round off error and distance is, approaching 0. But we're taking a sum of little expressions that represent the answers to much smaller questions, namely how much work does it take to add just that little bit of height to the building. Okay, so when you are answering one of these questions, step 1 is we write down the application in question as a Riemann sum. A Riemann sum is an integral. And then, to finish it off, sure, you plug into the fundamental theorem of calculus and get your actual numerical answer. So that's the problem-solving strategy, and it unavoidably involves Riemann sums. Okay. So here's what it would look like if we did it differently. Let's just momentarily consider this preposterous scenario where we redefine integrals to be area under a graph. Right, and then the fundamental theorem of calculus is over here now. Let me put a big X over here so that no one gives me a still shot and accuses me of, a still shot of the video and says, here's what Bray said. Because this is all wrong, okay? But let's suppose that we had set it up this way. And by the way, when I was in high school, this is what I thought. This is what my high school teacher told me. Why wouldn't I believe him? I thought integrals were defined as the area under a graph, and that you compute it with the fundamental theorem of calculus, and that Riemann sums is some ancient history, outdated, that's how they did it in the old days, aren't old people funny? Right? I don't know, that's the impression that I had, and it's really wrong. So let's think about how would you solve a problem? How would you compute this amount of work over here if that were the case? You would need to connect work to area. How do you do that? Right, how do you argue that, you want to compute work? Okay, work is kind of like area, you know what I mean? That's what you would have to do in order to be able to connect to an integral and then compute with the fundamental theorem of calculus. And it's not a reasonable connection to try to make. Now, students will try to get around this sometimes by saying, well, okay, the way you can connect work to area is to realize that, this work problem, you cut it up into slices and you think of the height as being like the height of a graph, and you think of the how tall is that little piece of the building, you think of that as like a width, and you just kind of, you effectively kind of make a sort of a poor man's Riemann sum argument. Right? Usually very sloppy. And usually involving nonsensical constructions such as infinitely small numbers, which aren't a thing. Right? So that's, by the way, if you're ever curious about that, that's a whole speech that I can give sometimes. There's no such thing as infinitesimals. But anyway, whatever that's worth. So there's this. It's a perverse construction. Again, this is how single variable calculus was taught to me. It's really importantly wrong, and it requires students to go to these awkward gymnastic, contortions to try to make any connections to real applications, things that they need to get answers to. Right? So we need to abandon this. This is totally wrong. This is how applications work. Right? Integrals are Riemann sums. Forget the area under a graph. It's a cute point of view. It's a nice application, I suppose. I will admit that in all of my years as an undergraduate second major in physics, I actually never needed to compute the area of anything. Really, it never happened. I mean, it's hard to come up with a scenario where you really need to know, hey, what's the amount of area there? Maybe if you're a painter, right? Right? You might need to know the area of something, but other than that, it's not a problem that comes up very much. So anyway, make sure you have this right point of view on what an integral is. An integral is a Riemann sum, and that's good because all of our applications, any application that you want to do with an integral, most naturally connects to a Riemann sum. It's going to make the arguments much more direct and convenient and intuitive, to be totally honest. Right? Okay. All right, so there's that speech. Okay, so a couple of examples. I mean, y'all know the area one, right? So, when you write down f of xi delta x in the area application, height is what the integrand is, and of course, let's see, we're also we're doing limit summation, and let's see here, how about yellow? Delta x we think of as width. And so here we're adding up a bunch of little pieces of area. The Riemann sum in question here is set up to address computing area. But here's a totally different application of a Riemann sum. I could, maybe I have this, I'm trying to, bad color choice, I'm trying to compute the mass of a one-dimensional rod. Y'all have probably seen these kind of questions in high school calculus classes, right? And you want to compute that. Density, mass per unit length at every point along the rod, and it's some function that's changing. It's not constant, right? Normally we just multiply mass per unit length times length. But if it's not constant, you can't. But you can argue that on any given little piece, density times length gives you the amount of mass in that one little piece. Right, in this one little piece, the amount of mass is that product. The total mass is the sum of the masses of all the little pieces that you chop the rod up into. Riemann sum. Yeah, is everybody good? Everybody happy? Okay. Notice that in this argument here, no discussion of area. Right, very importantly, what an odd little bit of math yoga it would be to say, well, think of the mass as being kind of like area. Right? It would be such a weird and pointless exercise. Okay, all right. Okay, so that's what I wanted to make sure everyone was straight about in terms of single variable integrals. Now I want to address the question of how are we going to go about defining multivariable integrals, and certain observations I want to make about all of the applications that we just looked at. We looked at two carefully, and then I made some hand-waving arguments about mass of the work it takes to build a building, etc. They're all different applications, but they all have certain features in common. In all cases, there's a domain and there's this function called the integrand. In all cases, I can break the domain up into little pieces. Of course, right? Less obvious. In all cases, the quantity that you're interested in is a sum over the smaller pieces. Now, whoa, slow down. This is not obvious. That not everything you would ever want to compute has this feature, right? If someone asks you, if someone says, here's a solid three-dimensional thing. I want to compute the surface area of this solid three-dimensional thing. If you were to say, okay, the way I'm going to deal with that is I'm going to take this and I'm going to chop it up into little pieces. On each little piece, I'm going to look at the surface area of that little piece. When you chopped, you made up new surface area. Right? So surface area of a solid does not have this feature. This is what I like to call an accumulating quantity. Some quantities have the feature that when you chop up the domain into little pieces, the total quantity is exactly the sum of the associated little quantities. Area under a graph has that feature. Mass of a rod has that feature. Surface area of a solid thought of as something that may or may not accumulate over the solid? No, it doesn't. Surface area does not accumulate over the solid. So you got to watch out, right? I mean, not every application has all the same properties. So this is a big one here, number 2, that the quantity in question is an accumulating quantity, as described here. We need, roughly speaking, we need continuity. So I had to put this in here, just roughly speaking, for continuity. And there's one other issue, but anyway, this is largely formal. And the last issue is that on the smaller pieces, the thing that we're interested in, be it area under a graph, be it the mass on a little piece of a rod, whatever, on each little piece, we're looking at a product, and specifically it's a product of the value of the integrand times the size of that piece. And notice that happened in both of these applications. It was the value of some integrand, maybe height, maybe density, whatever, but it was the value of the integrand, whatever the integrand was, times the size of the piece, so the width of that little piece of that domain, the length of that little piece of rod. Okay, so that's what all these applications have in common. And now the reason I write this down is because when we ask the question, well, I want to generalize, I want to come up, what should a double integral be? Well, I'm using the word integral. If I'm going to write something down and you declare it to be some kind of an integral, it better have something in common with single variable integrals. So we need to decide what is it that's intrinsically about integrals. What makes a single variable integral an integral, and what is a peculiarity of that idea to specifically the single variable context, right? So these are the 4 properties that I nominate as, all integrals have these properties. And so any kind of a construction that addresses questions that satisfy these 4 properties, that kind of a construction I'm going to call an integral. So we're going to apply that now to a 2-dimensional situation. We're going to reinterpret what we mean by size. Right? Notice this last property, there's a reference to the size of the piece. Well, in a Calc 1 class, size means, we're looking at an interval and we have a delta x that tells you how big is that little subinterval. The subinterval has a size. The size is the length. Length is intrinsically what size means if you're talking about a one-dimensional domain. That's how you talk about how big one-dimensional things are, is how long are they, what's the length. Okay, so if we're going to talk about a two-dimensional domain, the big thing to get accustomed to is that with a two-dimensional domain, if you chop it up into little pieces, the size of that piece is not a length. The size of that piece is area. Okay. All right. Okay, little applications I'm going to let you all work through there. Here's the question I want to start off with. Now, I emphasize, remember I made a big deal about how you can't think of single variable integrals as being area under a graph. And let me start just for the record. I do not want y'all to view double integrals fundamentally as being the volume under a graph, the volume under a surface. Okay, so please don't let this be your cornerstone sort of fundamental view of double integrals. And yet I have to recognize that, it's a really convenient starting question. This is going to be a good way to motivate the formula that we're going to write down for double integrals, but it's just for motivation. It's largely for, it's largely for motivational purposes. I can draw a picture. You can see all of the objects involved that we write down. It's great for intuition in that sense. But it's not general. Okay, so here's the question. We're looking at a graph. I'm going to compute this volume. And I propose that we do this. I propose that we take that volume and we slice it in a bunch of vertical slices in both different directions. Those who do a lot of cooking can tell me what that's called. Is that a dice or is that a julienne? Or I forget. We do a bunch of slices like this. Right? And then also, in addition, we do a bunch of slices like this. Right, slice it up in both different directions. There, I'll see what I'm talking about. And I claim that when you slice it up in both different directions like that, that's going to slice up the domain like this. and like this, resulting in a bunch of pieces of the domain that are little, I mean, you're going to be tempted to call them subintervals because that's, when you slice up the domain in Calc 1, they're called subintervals. These are not intervals. These are rectangles. So these are subrectangles. Yeah? Okay. So I claim that the question at hand of, how do you compute the total volume? That total volume, I think it's pretty clear, is the sum of the volumes sitting over all of these individual little pieces. That's just the geometry of the situation. Is everybody happy with that? So ultimately, this is going to break down as kind of a Riemann sum. We've taken the domain, we're going to slice it up in little pieces. We're going to argue that we need to add up a bunch of stuff that looks like, height, which is f of xy, because z is f of xy, times the area of the base, which I've kind of made a mess down here, but anyway, there's the area of the base, which, we're going to have to figure out what to call that. For the moment, let me just call that area. And we're going to be adding up in some sense. We're going to be adding up over all of the little subrectangles that we've chopped the domain into. Seemed like a reasonable strategy, right? Okay, so there's a few details to be cranked out. These are just details, but it's details that have to be. I have to write this down because if I'm going to, in case you haven't already guessed it, I'm working toward an expression that we're going to declare to be the definition of a double integral. And if I'm going to declare something to be the definition, everything that I write down has to be, precisely defined. So we have to go through this process, and y'all probably remember in Calc 1 that there was this whole thing where you let, you take your A and your B, and you slice up, and you call these points x0, x1, x2, blah, 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 and you note that delta x is b minus a over n. Y'all remember all that business? And xi is a plus I delta x. Yeah? You got to do the same thing now for the rectangle, just to have it written down. And this rectangle, I'm going to describe the rectangle as, by what are these x coordinates, telling you the left, right. What are these y coordinates, telling you the up, down. By the way, we have a notation for this. Y'all need to know about this notation. We say the rectangle is a comma b cross C comma D. So that tells you the range of values on this rectangle on the x-axis, and this tells you the range of values of the rectangle on the y-axis. So it's very convenient notation for representing rectangles. It's a little, cross. It's like a cross product, except it's not a cross product, but it's the same notation. So that's what that's what our initial rectangle looks like, and I can chop up in the usual way. So, notice that as you chop the rectangle, you are also chopping up this interval from A to B. We've already given names to the things that you get when you chop up the interval from A to B, so we already have x0, x1, x2, and that's all the same. That's just a rip-off from single variable calculus. And not that different for when you're slicing this way. When you're slicing like that, okay, it's not exactly the interval from A to B, but it's just C to D instead of A to B. And it's very analogous. And so the things that we write down there, they look just the same. A little bit different. Not very different. So delta y, y sub j, morally the same formulas. Okay. All right. So having done that, we can talk about a specific subrectangle, and keep in mind I need to be able to talk about specific individual subrectangles, such as this one. I'm going to call that Dij. It's in the kind of what you might call the ith slot over here on the x-axis, and it's in the jth slot over here on the y-axis. That's what these I and j are. Little subscript telling you, we're slicing this up into, we're slicing up the x-axis, this part of the x-axis into n subintervals and the y-axis into n subintervals, and if that little subrectangle corresponds to a certain subinterval on each one of those shadows, and so I need to know what the I and the j are, representing which subrectangle. So that's that notation. And there's a formula for how to write down exactly what Dij is. Here it is. We know what the shadow looks like on the x-axis, and we know what the shadow looks like on the y-axis. Okay. So apologies for all that details, but it's got to get written down so that we're precise when we write down. This is our strategy right here, where I want to add up height times area. I just need to be able to have precise formulas for all the things that I'm going to stick in to this strategy, and so we're pretty much done at this point. And here it is. You get that expression, right? That's the height. It's f. The area of the base is just, it's delta x times delta y. We slice type the x-axis. The width that is the width of the rectangle is also the width that is the width of a subinterval on the x-axis. So delta x times delta y gives you area. And here's our Riemann sum. Yeah? Okay, now what we've done here is we have successfully taken one application and we have written it as a Riemann sum. But this is our first Riemann sum over a two-dimensional domain. Right? I'm going to claim that there's lots of other applications, and we're going to see some in a couple of minutes here. There are lots of other applications that when you break them down according to the same big picture strategy, you get an expression that is equivalent to this. So the explicit motivation that I've given you for this expression is that it's the answer to a very natural question about volume under a graph. I ask you to believe me that it is also the answer to lots of other questions. And being so commonly useful, we're going to give this thing a name. The name is that this is a double integral of the function f over that domain, the rectangle domain D, and we're going to use this notation to represent it. All right, now the notation I think is pretty plausible. Notice that we use dA as a kind of a shorthand for delta A. That's a ripoff of what happens in single variable calculus. In single variable calculus, you have a delta x, and then when you write it as an integral, you write it as dx, right, to be suggestive of the delta x. Same deal here. Likewise, here we have there's a summation happening, and this says do a summation. We're going to use two integral symbols instead of one for reasons that have not come up yet, but we'll see those soon. But one motivation that you can take is that we are in fact adding up in two directions. So look at the summation that we're doing here. We're not just adding that one and that one and that one and that one and etc. and just 1 to n. 1 to n just takes you along the first slice, right? We're going 1 to n in the x direction, but we're also going 1 to n in the y direction. So there are literally kind of two summations happening here. Right? For each value of j, there are n different values of I. So, and it's going to turn out that this is true in more than just cosmetically. So I think the notation is pretty plausible, but anyway, this is the notation we're going to use. Whenever you see this, what that means is this. Said differently, whenever you find yourself with a question that can be written down as a Riemann sum, you can instead use this shorthand notation right as a double integral. Okay. Okay, by the way, just for your reference, sometimes that dA is written as dx dy. So, heads up. Okay, so here's an example. Let's go back to the mass of a sheet example. Oh, excuse me, I guess we haven't seen this one before. Here's a new question. Suppose I have a rectangular sheet made out of some non-uniform alloy where there's, lots of aluminum maybe over on this side, and there's more sort of, steel intermixed in over like that, and then there's a bunch of lead, maybe kind of like that. So they're kind of overlapping, wildly varying densities of this alloy that's created this sheet of metal. And I want to compute the total mass of this sheet of metal, and I know density is a function of position. How would I add this all up? I can't just take mass per unit area and multiply by area because the density is not constant, right? So the way we get around that is we say, look, it's wildly varying over large distances, but on any little piece, how much mass is in that little piece is just density that I know times area. And I just need to add that up over all the different pieces. Oh, here we go. Oh, gosh, I guess I'll zoom out. I need to take all these little masses and I need to add up over the entire rectangle all of those little masses, right? And when I plug in this formula, colors. When I plug in that formula for what delta M is, notice that the punchline is a Riemann sum. That looks just like the Riemann sums that we wrote down as the definition of a double integral. Right. So this is one of the. Sorry, I hit the wrong button. This is one of those situations like I was talking about where we have an application that doesn't have anything to do with volume. Right. This is about an area and mass. There's no volume in this question. Right. But the answer to the application is a Riemann sum, and we have a notation for Riemann sums. We write them as double integrals. Okay. By the way, there's a shorthand for this. People use this all the time. It's very convenient. Don't overinterpret from the shorthand. It's just a shorthand. But instead of developing the Riemann sum using Riemann sum notation and at the end rewriting it as an integral, what people tend to write is just this. So specifically, that sort of intermediate step in as you're developing your Riemann sum. Come on, you know that this is going to turn into that. So why don't we go ahead and do that now? Yeah, this is kind of convenient. Technically, we've never written down a definition of what that is, so this is just sloppy shorthand. But nevertheless, very handy and totally fine, and I encourage this kind of thing in Math 212. Okay. All right. There are several other examples in the rest of this section. Let's see here. Yeah, I have 20 seconds. Yeah. I'm going to let y'all read the rest of these examples. There are some details to be thought about. They are different kinds of applications of Riemann sums, aka double integrals. I want to leave you with one last parting thought, and that is that while I have written down a definition of a double integral, a glaringly missing part of the story is I have not yet told you how to compute double integrals, right? Where's the fundamental theorem of double integrals? You might be wondering. And we'll talk about that tomorrow. See y'all later.